All right, good morning. We're going to go over sections 4.3 and 4.4, and this section is called Other Common Functions and Transformations. We're going to use Desmos a good bit for this because Desmos can help us just illustrate things very quickly with our graphs. Okay, so the other common functions that we're talking, when we say other common functions, remember we just talked about linear functions and quadratic functions. And so this is kind of a continuation of that talk. And the other kind of functions that we're looking at are what we call power functions. Power functions look like this. So let's say f of x equals some constant a times x to the n power. And here we mean n being an integer that's positive. So n greater than 0, n an integer. We can also have negative power functions. We'll look at those. So the negative power functions look the same, but this time n is negative, but it's also an integer. Okay, those are the first two we're going to look at. Then we want to look at what I call the root functions. And the root functions look like this: a x to the 1 over n power, this time n being positive and an integer. So if you remember, the 1 over n exponent means like a root. So this is a times the nth root of x. That's what these look like. What do those graphs look like? We'll explain that, okay? And then lastly, what we want to look at here is absolute value functions. And the absolute value function, or what we mean by that, is a times, not the square root of n, sorry, the absolute value of x. And we want to look at the graph of that as well. Okay, so the reason I just listed them out like this is because we're going to look at what the basic form of these functions look like. And then in section 4.4, the book goes over how you can graph other functions that look like these, but just transformed a little bit. Okay, so what we first need to do is just look to see what these things look like in their basic form. And then after that, we're going to apply these different transformations and just kind of see what they look like from that perspective. Okay? All right, so let's start off with, let's call these 1, 2, 3, and 4. Let's start off with 1. And let's look at power functions. And I'm going to do this in Desmos first of all. All right, so let's get a list of a few of them. We could have these are, remember, x to the n power, n being a positive integer. So what could that be? Maybe like x squared. We've seen that one. That's a quadratic. We know what that looks like. Let's do x cubed. All right. Let's say, how about x to the 4th power? And I need to give myself a little bit more room if we're going to be doing some graphing. X cubed. How about x to the 5th? And then just for fun, why don't we go ahead and do the 6th and the 7th? And that sounds like a lot, but it's really not. Okay, so let me jump to Desmos, and we'll take a look at it. So grab my keyboard. Let me switch my video feed. All right, here we are at desmos.com. Again, you can get a free account or just graph even without an account. So let's start off, we said x squared. We know what this looks like. It's a parabola, right? There's my parabola. Okay. Now, if I do x cubed, I'm going to get something that looks a lot different. Why would it come down here below the x-axis? Well, if you remember, if I plug in a negative value in for x here, so for example, if I said negative 2 cubed, I get negative 8, because negative 2 times negative 2 times negative 2 gives me negative 8. That's why in the graph at negative 2, I'm way down here at negative 8. Okay, so let's not worry about x cubed at the moment. Let's go x to the fourth, see what happens. Well, so the blue graph, let me take the red off for a second. The blue one, which is x to the fourth, kind of looks like a parabola. It's just kind of flattened out a little bit around 0. If I put them together, you can see the difference. I wonder if I did x to the sixth, I get another parabola shaped thing, except it just flattens out even more around 0. It just makes me wonder, let's try another one. How about x to the eighth? What do you get? You get another parabola looking thing, it's just even flatter, okay? So the power functions for even functions, we could say, have this shape where they go up on both sides of, when I say go up, they're positive on both sides of the y-axis. All right, so let's take a look, let's go back to our notes, let's write that down, then we'll look at the odd powers. Okay, so here we graphed x squared, looked kind of something like this, just a parabola. And then as we got higher with these even powers, we saw, well, we still have a parabola shape. It just kind of flattens out a little bit around 0 and even more over higher powers. But the point is, for even powers, so let's say for even n, it's positive, and on, how would I say that? Well, the graph is positive on both sides of the y-axis. Right? It stays positive on both sides. Now, for odd powers, we saw x cubed, the graph of x cubed looks something kind of like this. Okay. What would you expect for the others? If I graphed x to the fifth and graphed x to the seventh, you're going to get something very similar, just like we did with the even powers, except you're going to flatten out more around 0. So something kind of like this. All right, x to the fifth, x to the seventh, even x to the ninth, it's going to be the same thing. So maybe just like we said for even n, the graph is positive on both sides of the on the y-axis. For the odd powers, we do what? On the left-hand side of the y-axis, we're negative. On the right-hand side of the y-axis, we're positive. So we say the graph is negative when, let's say when x is negative, and positive when x is positive. And these are not the two defining characteristics of these power functions. I mean, they still have this shape, okay? The even powers can have like a parabola type shape. The odd the odd powers kind of have this lightning bolt looking shape, right? You're starting out down at negative infinity, moving up to positive infinity. All right, sometimes this is described in this way. We call the end behavior. And we'll spend more time on the end behavior in chapter 5. But what you're thinking about is what happens as x approaches infinity. We can write it like that. X arrow infinity, that means x approaches infinity. or as x approaches negative infinity. So taking x to the fifth as an example, if I'm looking at the end behavior, what happens is x goes out this way. So that's x goes infinity. What happens? My function is going up. So as x goes out towards positive infinity, my function is also going towards positive infinity. And as x goes out to negative infinity, so this time x approaches negative infinity, what's my function doing? As I'm going further left, my function is getting further and further negative. So I can say my f of x approaches negative infinity as well. It's going down. And so if we're going to be a little bit more precise, and again, this is a detail we're throwing in, we'll cover in more detail in chapter 5, we could say that the even power functions, their end behavior is as x goes to infinity or negative infinity, the function f of x is going to positive infinity. And as I'm going out in either direction, I'm going to go up. And for the odds, for the odd powers, as x approaches infinity, I go up to positive infinity. As x goes to negative infinity, I go down to negative infinity. Okay, so that's a more precise way of what we're trying to say here. Okay, I hope that makes sense though. This is the basic idea behind power functions. All right, let's move on to our second group, which was negative power. Let's look at negative power functions. And don't forget, if you have a question, you can always leave it in the comments. All right, I'm trying to keep an eye on that. So this time for negative power functions, I have something that says ax to the n, but here n is less than 0, and we do want to stay in the integers. Okay, so here I have something like, what could I say? How about x to the negative 1 power? All right, and then from there, we might want to also consider x to the negative 2 power, and kind of break it up over odd and even like we did just now. How about x to the negative 3 and x to the negative 5? And then down here we'll say x to the negative 4 and to the negative 6. And let's go back to Desmos, kind of see what these kind of things do. What do they look like? All right, so here I'm back at Desmos. Let's get rid of these graphs. And I'm going to change the power from 2. Let's look at x to the negative 1 power. So negative 1 power. Whoa. I get this this funny thing. It's got 2 pieces to it. Okay. And so if you remember, negative 1 power means what? Reciprocal. So this function is the function 1 over x. Notice if I take off one of these, they're the same graph. They even graphed them in the same color. Okay. So if you think about 1 over x, if I try to plug in 0 in there, I get 1 over 0. If you remember, we can't have 1 over 0, right? That's undefined. So it makes sense that right at 0, you have this kind of this infinite divide. You cannot cross over the line x equals 0. Okay, and that's going to be true for all these negative power functions. So that's x to the negative 1. Let's let g of x be, how about x to the negative 2 power? Let's just see how it changes. All right, so take off f. All right, so it looks very similar to x to the negative 1, except with x to the negative 1 power, I'm down here in the third quadrant on the negative side of the x-axis. If I look at the negative 2 power, everything stays positive. That makes sense because remember, negative 2 power means 1 over x squared. X squared is always going to be positive. You can't square something and get a negative. So that makes sense that it would be that all the function values would be positive. So you kind of got this funny looking thing. So that kind of gives me an idea then. I think I know the whole story here. So if I let f of x be x to the negative 3, I'm expecting something like x to the negative 1, but kind of stretched in a certain way. Let's see. Yep, look at that. The shape is very similar. It just, the way it's contoured is a little bit different. And I bet if I did x to the negative fifth, we get something similar, just bent a little bit even more. And how about one more? Let's do x to the negative seventh. And we already know what this is going to look like basically, right? There you go. Okay, so these negative odd powers kind of have this basic shape. All right, now for the evens, so let me turn off the negatives. Here's x squared. I think we kind of understand what I mean, x to the negative 2 power. X to the negative 4 power is going to be the same thing, but bent a little bit more, just like x to the negative 3 power did the same thing for x to the negative 1. And I bet if I said the negative 6, it's going to look even, yeah, basically the same, just bent a little more. Okay, I hope this is making sense. So let's go back to our notes. I think we can get an idea of how these negative power functions operate. Okay, so looking at these things, let me do some quick graphs here. And I'm not trying to be overly precise, it's just an idea, just trying to get a basic idea of what's going on. For a negative 1, we have this shape like this. Okay, for negative 3, it's kind of the same deal. We're just bent a little bit more. And then x to the negative fifth, even more so. But they all have a similar shape to them, right? They occupy the first and the third quadrants. They can't cross the line x equals 0. Okay, for the negative 2, it's kind of a similar deal, except instead of in the third quadrant, I'm in the second quadrant. And the same for all my even powers. So these are how the negative power functions operate. All right, now let's quickly look at roots. Roots, so root functions. Root functions are what kind of things? Well, let's say the square root of x. How about the cube root of x and the fifth root of x? So again, I'm breaking it up over even and odd. And if I had the, well, actually I made a mistake there, right? The square root of x is the second root of x. So let's put the cube root of x down here. Let's change these to 4 and 6. And then here I have the cube root of x, the fifth root of x, and the seventh root of x. Okay, and I'll just kind of quickly go over what these look like. You can imagine that the square root, the fourth root, and the sixth root are going to have a similar shape to them, and you're right. Also remember that we can't plug in a negative x into the square root, right? Because you can't, what times itself becomes negative. Nothing in the real world, right? We have to go to the complex plane to do that, and we try to avoid that. So what these root functions look like is something like this. That's the square root of x. The fourth root is very similar, and the sixth root is very similar as well. They just change their shape a little bit. Okay, for the odd roots, you're basically taking the cube root of x, the x cubed, and flipping it sideways, so you get something like this. And for the others, they kind of follow the same pattern. You're just bent a little bit more around 0. And this is my root functions. These are my root functions. Okay. Now, for the absolute value functions, which is the fourth group we wanted to look at, if you remember, the way we define absolute value a long time ago was that the absolute value of a number, let's not call it f of x, let's say the absolute value of x is defined as x as long as you plug in something positive. So like the absolute value of 6 is 6. But if I plug something, or 0, we could say, but if I plug in a negative number, so if I plug in -6, the absolute value of that is 6. Now, one way you could think of that is that's -6. So we say that's a negative x for x less than 0. If you plug in a negative number, you have to multiply it by -1 to get back to the positive. Okay, so these kind of functions that are broken up like this are called piecewise defined functions. And what a piecewise defined function does is it looks like a particular kind of function just for a little while. In particular here, it looks like x when x is positive or 0, and it looks like negative x for x negative. It changes the way it looks. So the graph looks something like this. Let me think. It's 0, the absolute value of x is 0. For the positive values, it just looks like y equals x. What kind of graph is y equals x? Y equals x is a straight line with a slope 1, a y-intercept at 0, right? This is y equals x. Now, for x less than 0, I look like negative x. Y equals negative x is what kind of line? It's a slope with y equals -1 with an intercept at 0. So it's kind of the same graph, just an opposite version of it, if you want to say it that way. We get y equals negative x like that. And so together, this graph forms, let me get a different color. This graph forms f of x equals the absolute value of x. That's how you graph the absolute value of x. It's this V shape, which makes sense, I think, because if you plugged in, for example, if I plugged in -5 as an x, I get +5 as a y. If I plug in +5 as an x, I get positive 5 as a y, right? It's just the nature of this thing. Okay, great. Now, let's quickly talk about piecewise defined functions, and then we can talk about the transformations on these things. And what I'm going to do here is just look at an example and try to explain it with the example. And I'm going to use the book's example. Let me find it. Okay, so here's what we want to do. This is example 4 in your textbook. It says sketch f of x, which is -2x minus 2. And sometimes you say if, sometimes the if is just implied. If x is less than or equal to -1, and x squared if x is greater than -1. All right, so there's my graph. That's what I'm trying to graph. And see, this is a piecewise defined function. Less than or equal to -1, my function looks like this. If x is greater than -1, my function looks like this, right? So we've got these two pieces to it. Okay, but let me graph it, and hopefully this will make sense. Okay, so I think the easiest part to start off with is actually the x is greater than -1. It looks like x squared. So when I'm starting here at -1, -1 is kind of my dividing line where this function jumps from -2 minus x, -2x minus 2 to x squared, okay? So at -1, if I plug in -1 into x squared, that becomes a +1. And I'm going to put an open circle because I don't equal -1 at this spot, right? It's strictly greater than. But from there, I take on the graph of x squared, which is just a parabola, right? So you can think of this as kind of just y equals x squared. And that's if x is greater than -1, that's the graph I have. If x is less than or equal to -1, I have -2x minus 2, which is a straight line, okay? And if I plug in -1 into this expression, so let me do some scratch work here. -2 times -1 minus 2 gives me what? I get +2 minus 2, I hit 0. Okay, so this graph hits 0 at -1, and it is included because it's less than or equal to -1. Other than that, I have a line that would have a y-intercept at -2 if I could hit it, and it has a slope at -2, so it's going to look like this. And see, this is the line y equals -2x minus 2. And if you could project this thing forever, it would hit that y-intercept at -2, but I'm not allowed to do that. Why? Because the whole graph together, f of x, is these two pieces. This is f of x. And see, f of x looks like this straight line up until the point -1. And then after the point -1, it suddenly changes its behavior to look like x squared. Okay, so that's why we stopped our line at x equals -1. We came down, hit -1, and then we have this parabola from there on. Okay, I hope that makes sense. Piecewise divided functions are very useful. They can be kind of confusing at first, but we see these a lot. Okay, so an example of that would be if you're looking at tornadoes and you're measuring how strong a tornado is. So, we say sometimes this tornado was an EF3. Well, the way that's based upon is the wind speed. And I don't know the exact numbers off the top of my head, but you could say something like this. So the tornado gets measured 1, 2, 3, 4, or 5, and that's based upon its wind speed. So it could be something like if x is greater than 300 miles, so if my wind speed is greater than 300 miles per hour, then this is rated as a 5 tornado. And from there we can break down all these different categories in which to measure my tornado. That's a piecewise defined function. Okay? All right, great. Now, let's look at transformations. So if you remember, I think a good example to start with would be looking at the vertex form of a parabola, because we looked at these things already when we looked at parabolas. So we said something like this. We said f of x equals a x minus h quantity squared plus k. And I highlighted a, h, and k in green for a particular reason. I'll show you why. And what we said, this guy had a vertex of hk. Okay, now that's one way of saying it. I think another way of saying it is that we shifted x squared over h units, and that's in the left and right direction, and k units up and down. And what on earth do I mean by that? So let me give you an example. If I had f of x equals x minus 3 squared plus 1, and I want to graph this thing. Okay, I'm going to graph this function. All right, well, I know what this is going to look like instantly. So here I'm going to take x squared. This is just normal, good old x squared. And what I'm saying here is I have this h is positive 3, my k is 1. So from that, I can shift my graph over. Horizontally, I'm going to shift it over 3 units. So my new graph, let's move over 3 units. I moved this way 3 units, and then I moved up 1. So there's my new, where the origin was here at 0, 0, I have now moved over to 3, 1, and then I have the exact same graph. Now it makes sense to say then that the vertex is 3, 1, right? So what that tells me is that I started with a vertex at 0, 0, and then because h was 3, the x-coordinate of my vertex went from 0, moved over to 3. And since k is 1, my y-coordinate went from 0 to 3. Let me show you this on Desmos. Hopefully it'll be even clearer. And then we'll connect how this relates to our other graphs that we're looking at, the power functions, etc. All right, so I'm clearing off these graphs. All right, so let's look at, first of all, let's look at x squared. There we are. And then let me create another one that's in vertex form. We said x minus 3 squared plus 1. And notice what happened. This is what I'm trying to say. Look, if I zoom out enough, you can see that the green and the blue are really the same shape, right? They're the same shape. All I did was move the graph in the plane. And how did I move it? Well, since h was 3, notice that where I started at 0, I moved over to positive 3 in the left and right direction. And k was 1, so I moved everything up 1 unit. So I started here at 0, 0. Let me highlight. There's 0, 0, the original vertex. And now my new vertex is 3, 1. See, I've shifted over horizontally 3, up 1. If I did another graph, let's say x plus 2 squared minus 5. Okay, that looks way different, right? Well, not really. It's again the same shape. The black is the same shape. I just had a shift. My new vertex here, I can see, since it's in vertex form, my new vertex is negative 2, comma negative 5. See, right there. But instead of thinking about it in vertex form, think about it this way. Since h was a negative 2, I'm sorry here, this is x minus negative 2, right? Which means x plus 2. My h was negative 2. I shifted over from 0, 0, I shifted over 2 units to the left in the horizontal direction. And k was negative 5. I pushed my graph down 5 units. So I started out with this blue line, and then I just pushed it over 2 left, 5 down, and there's my new function. Okay, now where am I going with this? Let's change this now to x cubed. That's a graph we just looked at. And let's look at x minus 3 cubed plus 1. What do you expect is going to happen? It's going to be the same thing we just talked about. It's going to be the same curve, except I shifted everything over 3 units and up 1. 3 units to the right, up 1 unit. Okay, so the same transformation works. Look, let's do x to the 4th. So I do x to the 4th there, and now I'm going to look at x minus 3 to the 4th power plus 1. What do you expect? It's going to be the same graph. I just shifted over 3 units right to the right, 1 unit up. There it is. Look, same deal. Okay, so if I came down here to g of x and changed g of x to be x plus 2 to the 4th minus 5, what's going to happen? It's going to be this blue graph still, but I'm going to move it over 2 units to the left, down 5 units. And where's my graph? X plus 2, let me try it again. Oh yeah, I turned it off. So x plus 2 to the 4th plus 5. Make sure to turn it on. Oops, minus 5, right? There we go. It's okay to make mistakes. I'm living proof of that. All right, so here the blue is what we started out with. That's x to the 4th. That's kind of like our template function. And now we apply this transformation to it. The plus 2 means h is negative 2. So I move it 2 units to the left. The negative 5, k being negative 5 means I use 5 units down. All right, so let's try to make some notes of this, and we can look at some other graphs. Okay, so the way we could say that, let's do it this way. Let's say it this way. A transformation of functions let's say given f of x, the function g of x equals, I'm going to highlight some numbers here, a f of x minus h plus k is what? I mean, how do you graph that? It's just a translation of the graph. We move h units left or right. We use k units up or down. And the value of a, we didn't really look at that, but we did in the parabolas. Remember, the bigger the a was, the more condensed my graph becomes. We say it's stretched vertically. When a is between 0 and 1, it widens it out, okay? So we can say is a transformation of f by, let's say, a horizontal shift of h units, a vertical shift of k units, and then a stretching factor of a. That's it. Okay, so let me go to an example. Now that we've done these others up here, power functions, negative power, my roots, we've done all these. Now that I know those, I can graph a whole wide array of functions. Let me give you an example. And I need to come up to the top. Okay, let's go an example. Let's say example 5 maybe. We want to sketch f of x, which equals the cube root of x minus 1 plus 2. Gosh, I mean, before today I had no idea what the cube root of x minus 1 plus 2 would look like, but I have a pretty good idea now. So what I'm thinking of is, what's my template? My template graph is going to be the cube root of x. Right, that's the one I start out with. Do I remember what the cube root of x looks like? Well, it's an odd root, and the odd roots kind of do this thing. It's kind of this sideways S thing. It's like the cube root of x turned on its side, and it passes through the origin. And since it's the cube root of x, it's not too flat around the origin. All right, so that's my template graph. Now, we also need to identify in x minus 1, cube root of x minus 1 plus 2, let's see, a here is 1. So that means my stretch factor is not any different. And we'll look at an example of that in a little bit. H is positive 1. So that means I have a horizontal shift to the right 1 unit. And my K is positive 2. So I'm going to go up 2 units. Okay, so I'm going to take this same graph, start with the origin. Here's my origin. I said I'm going to move to the right 1 unit and up 2 units. So now my origin is there. And I'm going to just draw a little line here to help me get my symmetry good. It's going to look something like this. Okay, and maybe I didn't do a great job, but this is moving up to, well, this point here is now moving up to the right 1. So it's like right there. Okay, we have a shift like that. All right, let me do one more for you. And hopefully this is making sense. And let's throw in a factor of a because we haven't done one yet. So how about we graph? Oh, I don't know. How about let's do an odd power function. I mean a negative power function. How about g of x equals negative 2 x plus 1 to the negative 3 power minus 1. Okay, this one is a little tricky just because we have to keep up with a lot of stuff. So first, let's think about what our template graph is. That would be, wouldn't that be g of x equals x to the negative 3 power? Okay, that is right. So we're going to start off graphing that. X to the negative 3 power is a negative power function. It's going to look something like this. Remember, you have 0 here. We're going to kind of widen out, flatten out a little bit around the origin. We have that line at x equals 0 we can't cross. So it looks something kind of like that. That is x to the negative 3 power. All right, now from here, let's identify a, which is negative 2, h, which is negative 1, and k, which is negative 1. Okay, so the h means I'm going to shift everything over 1 unit to the left. The negative means to the left. K means we're going to go down 1 unit. So where the origin was here, now my new origin, if you will, is kind of right there. And I'm going to put the axes there just to help me visualize a little bit better where I'm kind of centering this thing around. Okay, now the negative 2, since it's negative, we're going to flip upside down. So the negative 2 flips everything upside down. So where I did have this purple line in the third quadrant down there, in my new graph, it kind of goes up like this. And where I did have in the first quadrant, now I'm kind of pushed down into like the new version of the fourth quadrant. And so something like that. There is my graph. And see, again, I took everything and shifted it over 1 unit to the left, 1 unit down, and then because of my stretch factor, since it was negative, I had to flip everything upside down like that. Okay, now this applies to the power functions, applies the absolute value function. We already saw an example with the roots. And truthfully, it applies to any function, even ones that we didn't cover or that we won't cover in algebra. All right, so this transformation, again, let me write down the general form of a transformation. If you have f of x equals a times g of x minus h, it means you plug in x minus h into the function, plus k. That's your general transformation formula. It's very powerful. A is a stretching factor, h is a horizontal translation, k is a vertical translation, and works just like that. You can use Desmos.com to check your work. Make sure you're doing it right. Guys, if you have any questions on this, I'd be glad to help, and I hope you have a great day. We'll see you on Wednesday. Take care.